This channel is Anil Yadav, and this is my AAT Tech Talk. This is my Tech Talk of the subject COA, that is Computer Organization and Architecture. My topic for today is redefining the role of the CPU and the era of the CPU GPU integration. We've seen the quick adoption of GPUs uh, as general computing engines in recent years, fueled by high computational throughput and energy efficiency. There is heavier integration of the CPU and GPU, including the GPU appearing on the same die, further decreasing barriers to the use of GPU to offload the CPU. Much effort has been made to adapt GPU designs to anticipate this new partitioning of the computation space, including better programming models and more general processing units with support for control flow. However, researchers have placed little attention to the CPU and how it must adapt to this change. Background: modern GPUs contain hundreds of arithmetic logic units (ALUs), hardware thread management, and access to fast on-chip and high-bandwidth external memories. This translates to peak performance of teraflops per device. We've also seen an emergence of new application domains that can utilize this performance. These new applications often distill large amounts of data. GPUs have been architected to exploit application parallelism even in the face of high memory latencies. Reported speedups of 10x Reported speedups of 10x to 100x are common, although other studies shows speedups over an optimized multi-core of CPU of 2.5x. These speedups do not simply imply that CPU performance is no longer critical. Many applications do not map at all to GPUs. Others map only a portion of their code to the GPU. Examples of the former include applications with irregular control flow and without high data level parallelism, as exemplified by many standard performance evaluation cooperation and teacher applications. Even for applications with data level parallelism, there are often serial portions that are still more effectively executed by the CPU. Furthermore, GPU programming currently requires considerable programmer effort, and that effort grows rapidly as the code maps less cleanly to the GPU. As a result, it is common to only map the GPU those portions of code that map easily and cleanly. Initial attempts at using GPUs for general purpose computations used corner cases of the graphics API. Six programmers mapped data into the available shader buffer memory and used graphics specific pipeline to process data. In various CUDA and AMD's Pro Plus platform added hardware to support general computations and exposed the multi-threaded hardware via programming interface with GPU hardware becoming flexible. New programming paradigms such as OpenCL emerged. Typically, the programmer receives an abstraction of separate GPU memory addresses space similar to CPU memory, where data can be allocated and threads launched. Although this computing model is closer to traditional computing models, it has several limitations. Programming GPUs still require architecture-specific optimizations, which impact performance portability. There is also performance overhead resulting from separate discrete memory used by GPUs. Recently, AMD fused accelerated processed units. Uh, AMD, Intel, and ARM have released solutions that integrate general purpose programmable GPUs together with CPUs on the same chip. In this computing model, CPU and GPU can share memory and common address space. Such sharing is enabled by the use of an integrated memory controller and coherence network for both CPU and GPU. This promises to improve performance because no explicit data transfers are required between CPU and GPU, a feature sometimes known as zero copy. Furthermore, programming becomes easier because explicit GPU memory management isn't required. Benchmarks. Over the past few years, a large number of CPU applications have been ported to GPUs. Some implementations almost completely map to the GPU, while other applications only maps certain kernel codes to the GPU. For this study, we examined a spectrum of applications with varying levels of GPU offloading. We relied as much as possible on the published implementations so that the mapping between GPU code and CPU code wouldn't be driven by our biases or abilities, but rather with the collective wisdom of the community. We made three exceptions for particularly important applications where the mapping was clear and straightforward. We performed our own CUDA implementations and used those results for these benchmarks. Use three mechanisms to identify the partitioning of the application between CPU and GPU. First, if the GPU implementation code was available to the public domain, we studied it to identify CPU map portions. If the code wasn't available, we obtained the partitioning information from publications. Because with the different publications tend to use different processor baselines and GPUs, we normalized them to a single core AMD Shanghai processor running at 2.5 GHz and NVIDIA GTX 280 GPU with 1.3 GHz shader frequency. We use published spec rate numbers and linear scaling of GPU performance with a number of streaming multiprocessors and frequency to perform normalization. We also measured the CWC. Also measure the collected statistics for pure CPU benchmarks with no public known as CPU manipulation combined with previously mentioned benchmarks. This gives us a total of 11 GPUs, CPU only benchmarks, and 11 GPU heavy benchmarks, and 11 mixed applications, where some of not all the applications is mapped to the GPU. We don't show the CPU only benchmarks in table 1 because no CPU GPU mapping is done. So these are the benchmark stuff. Experimental methodology. Here we describe our infrastructure and segmentation parameters. The aim here is to identify the fundamental code characteristics. Experimental code characteristics. Since when possible, measuring LLB and factoring load stores and branches into types, rather than always measuring particular hit rates. We didn't account for the code, etc. Here we examine the characteristics of code executed by the CPU both without and with GPU integration. For all of our presented results, we partition applications into three groups. Those where no attempt has been made to map code to the GPU, those where partitioning is a bit more evenly divided, and those where nearly all code is mapped to the GPU. Now we first look at CPU time. What portion of the original execution time still gets mapped to CPU, and what's the expected CPU time spent running on that code? Then we then go to the examine other dimensions of that code that still runs in the CPU. To identify the CPU's utilization and performance critically after GPU offloading, we calculate the percentage of time in CPU execution after the GPU mapping takes place. We use initially the supported speeds from literature for each GPU mapping. The first bar in figure 1, etc. ILB captures the instruction stream's inherent parallelism. It can be thought of as measuring the dependence critical path through the code. For out of order processes, ILB depends heavily on the window size, the number of instructions the processor can examine at once, looking for possible parallelism. As figure 2 shows, in 17 of the 28 application, ILP drops noticeably, particularly for large window sizes. For Swim, Milk, CFD, MGrid, and Fluid Animated drops by almost half. So this is the diagram, and have a look at it. So when I look on the figures, this is another figure. Branch resource. We classify static branches into four categories: bias, patterned, correlated, or hard. Overall, we see significant increase in hard branches. The fact the frequency of hard branches increases by 65%. The increase in hard branches the overall average is only a result of two factors: the high concentration of branches in the CPU only workloads and the marked increase in the hard branches in the next benchmarks. The hard branches are primarily replacing the reduced pattern branches because the say easy branches are reduced by a small amount. This is another figure. Impact on CPU design. Good architecture. Oh my god. So an external for the construction, education stream, etc. etc. Load and store prefetching. Memory access will continue to be perhaps the biggest performance challenge for future processors. Our results touch particularly on design of future prefetches will heavily influence CPU and memory performance. Stride-based prefetches are commonplace on modern development. Vector instructions. SSC instructions haven't been rendered unnecessary, but they are certainly less important. Thank you. That was my TED talk.